Hello friends, welcome back. In the last lecture we learned resampling. In that we first learned downsampling and then learned decimation. Now the second concept to change the sampling rate, to increase the sampling rate, that is upsampling, is the second concept that we are going to learn today. Okay, and after that we'll learn how why interpolation is necessary and why it is done. So first take one example, signal x of n. X of n is suppose a signal 1, 2, 3, 4. Okay, and we want to upsample that. So y of n is an upsampled version, okay, by a factor of 3, say. So for a single sample, we want 3 samples like this. So y of n, I will draw this. So I'll take the first sample, then add 2 zeros. Okay, so for this single sample, I'm taking 3 samples. Then 2, then 2 zeros, then 3, then 2 zeros, then 4, then 2 zeros. So if I want to upsample the same signal by a factor of 2, what will I do? I will insert only a single 0. So upsampled by signal by a factor of 2, the same signal will happen to be 1, 0, 2, 0, 3, 0, 4, 0. Okay. So like this we upsample the signal. So we're actually changing the sampling interval to some different sampling interval. Okay. So we'll draw the signal and let us see what happens to the signal. So say for example this is the signal which is already sampled signal, which is having some sampling time interval Ts. So let us call the signal x of n the input signal, and we want a signal which is having zeros inserted in between. So let us say this y of n is an upsampled version of x of n. So for example, we'll insert 2 zeros like this, and then this sample. So this new sampling rate is Ts, sampling interval is Ts dash. So here we'll insert zeros like this, it will go on, and this is y of n. So actually saying we are inserting zeros, so the signal is actually expanded version if you are going to deal with the same rate. So we are increasing the number of samples, so we are expanding the signal. So it can be expressed y of n in terms of x of n as x of n by l. As we are increasing, we are expanding the signal where n is equal to 0 plus minus l plus minus 2l. So multiples of l, we are having the original samples, and otherwise we are having zeros. So it can be written like this. So let us now try to find out the expression for the spectrum of y of n. Okay, so we want to check what happens to the spectrum when we change the sampling rate, when we upsample the signal. So let us take discrete time Fourier transform of the signal. Y of e raised to j omega is equal to summation n varying from minus infinity to infinity y of n e raised to minus j omega n. So let us write what is y of n. It is x of n by n e raised to minus j omega n. Okay. Now let us take n by l is equal to p. So n is equal to l into p. And let us try to put this. So y of e raised to j omega, here it will become, let us say p is again starting from minus infinity to infinity. If you put these values, it is coming out to be minus infinity to infinity. So x of p e raised to minus j omega l p. And let us take one bracket here. So you can observe this is the Fourier transform of x of p. So it will be x of e raised to j omega. But omega is changed to omega L. So we can write it as x of e raised to j omega L. Okay. Because here omega L is existing. That's why omega L at this point. So let us try to draw the spectrum. Let us see what happens to the spectrum. And as you observe here, omega L. So omega L, a factor is multiplying to the frequency. So we'll obviously observe a compressed version of the spectrum. In the downsampling, the spectrum was spread. Okay, so here let us take a spectrum. Okay, so this is x of e raised to j omega input spectrum. So let us assume this is having a shape like this. So it is, as it is a discrete time signal spectrum, it will be having its images like this. Now here we'll draw spectrum of y of e raised to j omega. Of y of e raised to j omega is x of e raised to j omega L. So it is a compressed version. So compressed by a factor of L. So let us take L is equal to 3. So instead of, so this point pi will occur at pi by 3. Okay. So here pi by 3 is there. This is pi by 3. So at pi, which point will happen to be there? 3 pi point. Okay. So at pi we will observe 3 pi point. Okay. So this will be compressed like this, and this 3 pi will come to this. So this will be also get compressed, and it is observed like this. Now at this point also, this minus 3 pi will come to minus pi. So we are observing 3 copies from the minus pi to pi. Okay. Now similarly we can observe additional copies instead of the single copy in between this duration. Okay. So it is like this. And here no amplitude change is not there. So if the amplitude is 1 here, it is also the same. So it will be like this, and a more number of images on this side. So let us draw on this side also. Okay. And this is minus 2 pi. So we are observing a lot of images on both sides. So that images are unwanted images. So there is a problem of we can call imaging. The problem of imaging is occurring in upsampling. We were observing a problem of aliasing in case of downsampling. What was happening at that point? The images and the original spectrum, these were mixing with each other, and aliasing was happening at downsampling. But in case of upsampling, we are observing a lot of images. So there is a problem of imaging, we can say. Imaging problem happens with upsampling. So we don't want this kind of images. So what we can do, we can low pass filter the extra images. Okay. I'll drop this now. So we want only this middle part. So we can use a low pass filter of frequency pi by 3. This is my pi by 3. So we can call it h of e raised to j omega. So we don't want to change the amplitude. We just want to uh, capture the central image original copy. Okay, for this we'll assume it is around 2 pi. So this will also come, and around 2 pi minus 2 pi, this is around 2 pi, and so on. So after passing through this low pass filter, h of e raised to j omega with cutoff frequency pi by 3. So if L is equal to 3, we are taking pi by 3. If L is some different number, we can take that number. So it is always, cutoff frequency is always related to this factor L. So it is pi by L. So after passing through this low pass filter, what we'll get? This image, this version of this image, and this extra images, these are removed. Okay, so we are getting a compressed version of the original spectrum like this. So I'll write the frequencies here. This is pi by 3 minus pi by 3. The center point is 2 pi. This is minus 2 pi. So this is the y of e raised to j omega after interpolation. You can see this stage is called interpolation. So interpolation is what? It is passing this upsampled signal through a low pass filter of the specific frequency, which is related to this upsampling factor. So pi by L is the cutoff frequency of this low pass filter. So we'll draw a block diagram of this. I hope you have understood this, what happens in upsampling. For upsampling and downsampling, these are two very important operations, and these can be used consecutively one after the another to get the various sampling rates, and it is also used in filter banks. So block diagram, let us say x of n is the input signal and we are upsampling the signal. So you have to use the low pass filter after upsampling because the images are going to happen after, these are going to appear in the picture after upsampling. So at this point images will occur. So we are using a low pass filter of cutoff frequency say pi by L. L is the upsampling factor. So here is the final output signal y of n, which is interpolated signal. So we are using this low pass filter to get rid of extra images which are happening coming into picture because of upsampling. Thank you.